Welcome to week 6, video number 6. Can you believe we are already at midterm? This week we are going to learn about radical expressions, functions, and complex numbers. I made this table for you. I actually think you probably already know a lot of these. Perfect squares, perfect cubes, perfect fourths. You probably should memorize some of those. And then I actually have a column for variables and radical variables as well. So if you look at the one that I have circled there, that is a radical expression. The little number on the outside is the index. The squiggly long division sign is the radical, and underneath is called the radicand. The cubed root of x to the third is x. You divide the exponent by the index, and that's how you unradicalize those. That's a word I just made up, I think. Anyways, down at the bottom in that white box, we have the fifth root of x to the 12th. In order to simplify that, we have to break that down into two pieces. The fifth root of x to the 10th, which is a perfect fifth root because 10 is a multiple of 5, and the fifth root of x squared is kind of the remainder. The fifth root of x to the 10th breaks down to x squared when it comes out from underneath the radical, and the second part of it we leave just as it is. For this week, I thought I would do just some book examples for a change of pace. So 560, here's some examples for you. The square root of 49 equals 7. Number 5, look at the plus or minus in front. We have to make sure that comes into the answer. And 81 is a perfect square, so the square root plus or minus the square root of 81 equals plus or minus 9. Number 13, we have the negative cubed root of 216. You should recognize 216 is a perfect cube, and my answer would be negative 6. 45, the cubed root of 100. If we want to estimate what that is, we have to trap that between two perfect squares, and we are two perfect cubes, and we would trap it between 4 cubed, which equals 64, and 5 cubed, which equals 125. So we can estimate the cubed root of 100 to be about 4.5. 53, now we're going to add some variables into this. So I have the square root of a to the 4th and b to the 6th, or times b to the 6th. They are perfect squared exponents because they are multiples of 2. So my answer here is a with 4 divided by 2 and b to the 6th divided by 2, which equals a squared and the absolute value of b cubed. Please read in your book about when to use absolute values. Because b cubed is an odd exponent, if b happened to be a negative number, my answer would turn out to be a negative number. And the square root of any number or any variable cannot be a negative number. Page 573, some examples from there are the square root of 50 equals the square root of 25 times the square root of 2. I'm looking for perfect square factors. And then I can simplify the first half to 5 and leave the second half in radical form. Number 35, this is a little bit more difficult, a little more steps. So I broke it down into tiny baby steps for you, so hopefully that will help you. I know that 56 is 8 times 7, and 8 is a perfect cube. So I broke that into the cubed root of 8 times the cubed root of 7, and x to the 6th is a perfect cube. Y to the 5th is not, so I broke that down into y to the 3rd and y to the 2nd. And z to the 4th is not a perfect cube, so I broke that down into z to the 3rd power times z to the 1st. Now, the first term, or the first factor, is the cubed root of 8, which is 2. I leave the radical form, the cubed root of 7, as it is. The cubed root of x to the sixth is x squared. Leave the radical form. I'm sorry, the y comes out as just y. And then the second part stays in radical form. The cubed root of z to the third is z to the third, is z. And then I leave the radical form of the last part. Then I simplify, and I get 2x squared times yz times the cubed root of 7y squared z to the first. And I really don't need to write the first power. We assume that a variable is to the first power if there's no exponent. Continuing with some more examples from 573, now I'm going to look at the quotient, a radical quotient. Radical quotients can be broken down into the radical in the numerator and the radical in the denominator. And in this case, our denominator is a perfect square. So the square root of 9 is 3, and the square root of y to the fourth is y squared. Our next example, number 69, is the cubed root of a to the fifth over b to the seventh. I'm going to use the same procedure and break it down. Now I'm making it all under one radical, and I'm going to make it the cubed root of a to the third times a squared over the cubed root of b to the sixth times b, breaking it down into perfect cube factors. The cubed root of a to the third on the top comes out as a. The second part stays in the radical. The cubed root of b to the sixth in the denominator comes out as b squared, and the second part stays under the radical. Remember to divide the exponent by the index. The next page we're going to look at for examples is page 584. Number 9. Now we are adding radicals, and in order to add radicals, the radicands must be the same. If that's the case, then we can just add the numbers, the like terms, on the outside. And we have 8, -2, and 3, and that gives us 9 square root of 6. Number 23, now, if you look, our radicands are different. So your goal is to get them to look the same. And if you look at the middle term, the radicand is 2w squared. Is it possible for us to turn the first and last term into the same radicands? Yes, it is, and this is how we're going to do that. We're going to break down the cubed root of 16w to the fifth as the cubed root of 2w squared times the cubed root of 8w cubed. The second term we're going to leave exactly as it is, and the third term we're going to change that into the cubed root of 2w squared times the cubed root of w cubed. Now I have created some perfect cube radicands that I can eliminate the radicals on those. So in the first term I have 2w, the cubed root of 8w cubed came out as 2w, and my radical piece is the cubed root of 2w squared. In the second one, I leave it exactly as it is because my radicand is the cubed root of 2w squared. On the last one, and remember I'm subtracting that piece, the cubed root of w cubed comes out as w, and my radical piece is the same. Now I can combine my like terms, and that gives me 3w times the cubed root of 2w squared. My next example is number 71. Now I have a radical in the denominator position. We actually can never leave a radical in the denominator position, so we're going to multiply by a very special one that we call a conjugate. And the conjugate that I'm looking for is something that's going to make the denominator a perfect cubed radical. So if I multiply by the cubed root of 2 over the cubed root of 2, you will agree that that's 1. I get the 3 cubed root of 2 in the numerator and the cubed root of 8 in the denominator. A perfect cube. 8 is a perfect cube. So that gives me the same numerator, and I can simplify the denominator to be 2, just by multiplying by that special one that's the conjugate. My next example is 81, and now I have a binomial radical, and I'll just stop there. I'm going to multiply by a special conjugate again, and if you look at this one, you have to agree that that conjugate is 1. It's the same thing over the numerator and the denominator are the same thing. Now that should look very much like the binomials that you were multiplying in last week's lesson. Now we have the sum and difference, so that's the reason we chose the square root of x minus the square root of y as our conjugate. And we'll FOIL the top, and you see what we get in the numerator. And look at the denominator. Now we have the square root of x squared minus the square root of y squared. And simplified, the numerator, the square root of x squared comes out as x. The square root of y squared comes out as y. But look at the denominator. Now we have no radicals in the denominator, which was exactly our goal. We're going to 593 now to see some examples from that page. And this says to solve and check. Now we are going to actually solve radical equations. In number 7, you see that that's set equal to 0. For this particular problem, what we want to do is isolate the radical on one side by adding 4 to both sides. And now we square both sides. Excuse me. Squaring eliminates my radical, and I get 2x plus 4 equals 16. Now it's a simple two-step equation. I solve that, I get x equals 6, and typically we put solutions in braces. Now I'm going to do a check by plugging that 6 back into the original equation where x was, and I'm going to find out if that's true. So when I replace the x with 6, I get the square root of 16 minus 4. Is that equal to 0? And yes, it is. 4 minus 4 equals 0, and that does check. Our next example is 33, and this one's even easier. Because we have a radical on both sides, all I have to do is square both sides. That eliminates my radicals. I have 2x equals x plus 1. Solve that, and I get x equals 1. Now I'm going to check that by plugging the 1. And remember, the solution's usually in braces. When I plug that 1 in, I'm going to get that the square root of 2 equals the square root of 2, which is true. Now for our last slide, we're going to look at page 603, some examples there. Number 21, now we are looking at rational exponents. So I have 8 over 27, the quantity of, that means in parentheses, raised to the 2/3. We are going to change those into radical expressions. Now keep in mind, the numerator of your rational exponent is going to be the exponent, and the denominator will be the index in your radical expression. So I change 8 over 27 raised to the 2/3 to be the cubed root of 8 squared and the cubed root of 27 squared. I'm going to take baby steps here. The cubed root of 8 times the cubed root of 8. I wrote it like that because you should know that 8 is a perfect cube, as I did the denominator because 27 is a perfect cube. That gives me 2 times 2 on the top and 3 times 3 on the bottom, which equals 4/9. My next example is 30, and that's 16 raised to the negative 3/2. The thing with this is that it's a negative exponent. The negative exponent, remember from your rules of exponents, say that if you have a negative exponent, you take the reciprocal of the base, which would be 1/16 and 1/16, and then your exponent becomes positive. Now keep in mind that the numerator is your exponent, the denominator is your index. I'm going to change it into radical form, and I get the square root of 1 cubed over the square root of 16 cubed, which gives me 1 over the square root of 16 times 16 times 16, baby steps again. The square root of 16 is 4, so that gives me 1 over 64 because it's 4 times 4 times 4. The next one we're going to look at is 64. Now we have a whole bunch of things going on. We have negative exponents, we have rational exponents, we have power to the power. So the first thing I'm going to do is get rid of the parentheses in the numerator by multiplying the 6 times the negative 2 and the 6 times the negative 1/4. Now I'm going to use the rule of exponents that say if you have like bases, you can subtract those exponents. But you must remember to subtract the exponents where the larger exponent is. So if I look at the w's, my w to the negative 8 is larger than w to the negative 12, so I want to subtract in the denominator position. Z to the 1/2 is larger than z to the negative 6/4, so I'm subtracting in the denominator position again. When I do that, I take everything from the numerator, I must put a 1 up there. Simplify that subtraction. Please be careful of your signs and fractions. That gives me 1 over w to the 4th, z to the 2nd power. Another example is number 83, and this is a relatively simple one. We have the quantity of 3x raised to the 2/5. Keep in mind, 2 is the exponent, 5 is the index. I'm going to take the 5th root of 3x squared equals the 5th root of 9x squared. Because I'm squaring that radicand, and 3, the base, must be expanded, I square that 3, that gives me 9, and square the x, that gives me x squared. That can't be simplified any further than that. The last page I'm going to do any examples for you are from page 612, and you probably should read some of this, at least, if you're not familiar with imaginary and complex numbers. Our first example are actually complex numbers. Complex numbers are a real part and an imaginary part put together. In standard form, it's always the real part first and then the imaginary part. When you're adding them, you're going to think about the imaginary part that we designate by a scripted I, just like you'd think about a variable. So I'm going to add the 3 and the 4 and the negative 7. And I'm going to add the I and the 5i and the negative 7i, and that gives me 7 minus I. This is in standard form, and standard form means the real part, the 7 is first, and the imaginary part is then after the real part. That's number 19. Number 20, now I'm going to multiply a monomial imaginary number times a binomial complex number. So I have to distribute, and that gives me 12i plus 30i squared. I hope that in the information you looked over in the book, you learned that I squared is equal to negative 1. So that gives me negative 30, which I'm going to move to the front of this expression because I want it in standard form, and standard form is the real part and the imaginary part to its right. Number 41, now I'm going to multiply two binomials. So I'm going to set them up side by side. I'm going to FOIL them, and I'm going to get 49 minus 21i minus 21i plus 9i squared. I'm going to combine my middle terms and change my I squared into negative 1 times 9, and then I'm going to add 49 and negative 9 and put it in the first place because I want it in standard form, and my answer is 40 minus 42i. Now I have a complex quotient. I'm going to use the conjugate system again. I must come up with a special one that would eliminate the complex number in the denominator position. My conjugate is going to be the opposite sign of the denominator. So I'm going to multiply by 3 minus 4i over 3 minus 4i. I FOIL the top and I FOIL the bottom, the denominator position. And what happens, because it's the sum and difference, my middle terms would cancel in the denominator. And remember that I squared is negative 1. Negative 1 times negative 16 is positive 16. I'm going right through the denominator here, and that gives me 25. When I simplify the numerator, I have positive 16i, which changes to negative 16, combined with the 9 gives me negative 7, minus 24i over 25. This is a totally acceptable answer. However, the book will almost always write it in two different pieces, negative 7 over 25 minus 24 over 25i. Because of standard form, they want the real part first and the imaginary part second. Now, the best part of this whole lesson is simplifying powers of I. Powers of I to the 35th, I to the 125th, whatever you want to do. If I break that down into, first, the powers of I to the 4th raised to a power, because I to the 4th is equal to 1, I to the 4th raised to the 8th is I to the 32nd, which is all 1. What I'm left with is I to the 3rd, and I to the 3rd actually gives me my answer, negative I. And all you have to do for this is break down the power to the largest power of I to the 4th. The remaining power is your answer. You must remember that I equals I squared equals negative 1, and I cubed equals negative I. That's the end of our lesson for week 6, video 6. And remember, this is midterm week, so start preparing right away. You should be reviewing your homework, and your midterm test will be due Friday at 4 p.m.